All right, welcome to another exciting episode here of AP Chemistry, Advanced Level Chemistry here at Spain Park. Today is Thursday, February the 5th. Sixth. Day late and a dollar short. Today is February the 6th. Okay, and Austin, what are they supposed to do if they're liking these videos?
Hit that like button, hit that subscribe button, and ring that notification bell if they never want to miss another chemistry episode.
That's exactly right, because they're so darn exciting. And if you ever have any issues sleeping, these are also a great cure for that. All right. So, as evidenced by the way y'all look here in about 20 minutes. All right. So, when we're looking at this, a lot of this is going to be review, but we're going to go through and talk about naming compounds and writing formulas for compounds. But we got to get some things straight first. And so today is going to be all about just kind of clarifying, getting us all on the same page and making sure we understand the definitions. And then tomorrow we'll get into actually beginning to name and write formulas, first for ionic compounds, and then for covalent compounds, and then for acids. And we just have to be able to identify when it's an acid, and it's got its own set of rules for naming for acids. So we're going to have 3 different sets of rules, but it's going to be pretty much follow the yellow brick road. I'm going to give you a flow chart to help you with your thought processes on that as well. But when we first come through, we want to define a chemical formula. So if I say C6H12O6, what is that telling me?
Has carbon and hydrogen and oxygen.
So it's telling me the type of atoms or elements that are involved. What else is it telling me?
How many?
How many? Okay, so the chemical formula, okay, describes the kinds and numbers of the elements in a given compound, given substance. Okay, so C6H12O6 tells me that there's 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in glucose or in fructose. Okay? Now, we have different types. We have molecular formulas and empirical formulas. We just took the quiz, found the empirical formula, then we found the molecular formula. Okay? So I'm going to go down. I'm going to skip this first one here. Molecular formulas. What kind of compounds do molecular formulas describe? Covalent, right? And how do we know it's a covalent compound?
2 nonmetals.
2 nonmetals. Okay? So use to represent covalent molecular compounds. Okay? And you should know by now, but if you want to put out in the parentheses out to the side, 2 nonmetals. Okay? Now, what does this show? Very redundant right here. What does this show?
Number and type.
Number and types, or number and kinds, whatever number. I'm going to say kinds just to be familiar. But what's the smallest part of a covalent compound?
Molecule.
A molecule. In a molecule of a compound. So this is deep, okay? This is why you're at advanced level right here. Okay, a molecular formula describes the ratio in a molecule of the compound.
I never
Okay.
would guess.
Yeah, I know, that's deep, okay, but hey, I know it's late in the day, but hey, we just got to soak it in. Okay, so the molecular formula shows how many atoms and the types of atoms and how many in a molecule of the compound. What doesn't it have to be? Well, let me help you, give you a hint here. What is the definition of an empirical formula?
The smallest version.
Okay, but it's the what whole number ratio?
The
The smallest or simplest, right? Okay, ratio of, and what, again, another deep question. What type of particles compose an ionic compound?
Ion.
Say it again.
Ion.
Ions. The ratio of ions, not atoms. Notice that this says the number of atoms in a molecule. This is ions in an ionic compound. Okay, it's the simplest ratio. So what does a molecular formula not have to be? Okay? How did we find the molecular formula from the empirical formula?
You took the molecular mass and divided by the empirical formula.
And got a
Ratio.
whole number, and then you multiplied it, right? So what didn't you have in a molecular formula? If an empirical formula is the simplest whole number ratio, what does the molecular formula not have to be?
The simplest.
It does not have to be the simplest ratio. But describes the molecules as they exist in nature. For instance, C6H12O6. It's not the simplest ratio. It's the way the molecule exists. We talked about H2O2. Okay? Hydrogen peroxide. That's the way the molecule exists. Now, it can be the simplest ratio. We have water. That's the way the molecule exists. That is the simplest ratio, but it's also the molecular formula as well. Okay? So the thing is, it just doesn't have to be the simplest ratio. It's how the molecule exists. But for this, it's just going to be the ions present. So we're going to always just going to say, we know NaCl. It could be possibly Na2S. It could be MgCl2. Could be Al2S3. Just some simplest ratio. And we're going to learn, how do we know what those subscripts are going to be? That's going to be our goal, kind of this unit. How do I know what to put for the subscripts, and how do I name it and all that? So you're going to have a sense of power. You're going to be able to look at the back of the ingredients and see all these names, and you'll be able to at least name 2 out of the 20. Because most of them are these big old long organic names that, you know, a lot of them are just common names. All right, so most of this is nothing new, nothing overwhelming, nothing that we haven't talked about before, nothing that you hadn't seen before, so nothing earth-shattering on that. So do we all have this all written down so I can start with a clean slate here, literally?
What was the last line I've written down?
Oh,
I was about to say that. I was just like, I can do this real quick, but then you went really fast.
just look, what,
I've never seen it
here?
for anyone. Okay. Alright, got it.
Okay, got it?
Yeah.
All right,
It is bad.
yeah.
It was just one at the damn
Okay,
yeah.
I try not to be to where I go too fast, but, okay.
No, I
Now-
think you would erase that fast. Like you had your hand was going, I was like, okay, I just didn't like did that.
Well, you gotta speak up.
Okay.
Gotta be quick. All right. So, we gotta get some things kind of just definitions under here, and this is a big one right now. Up here is a chart of polyatomic ions. What does that word mean? Polyatomic. Okay? Polyatomic ions. Okay? They're tightly bound groups of covalently bonded atoms. Notice that almost all of these are non-metal with a non-metal. There are a few metals in there, but they're transition metals, and with the higher oxidation states, they end up having some covalent nature in their bonding. Most of them are just going to be covalently bonded together, but they act as a single unit. Okay? So they're going to kind of go together. And I always think of this like way back when being like 4 or 5 years ago, and then for 10 to 15 years before that, they had the student gate. You know where the football players come in and where the band comes in? That gate. That used to be where all students had to come in, and I would check that they had the activity card, and they would come in, and I would kind of monitor that. So all students came in through that gate. Okay, and I worked that gate for years. Okay, and so I would always see these groups of junior high girls, posses of 4, 5, 6 girls, but wherever one went, they all went together. The group never broke up. They never saw a single play of the football game, but they had a great time while they were there just running around chasing. Usually they're chasing boys and boys are chasing them, and, but the group always stayed together. That's what these polyatomic ions are. It's that group that just stays together. They act as a single unit. So when I look up here and I see SO4 sulfate, okay, when that reacts in a reaction, most of the time, it's not going to react as a sulfur and an oxygen. That SO4 is going to act like a single unit, and it's going to just stay together and then just kind of swap instead of it just, sulfur and oxygen breaking apart and doing whatever. It's just going to act like a single thing. And when we start forming these compounds, we'll see how that works. Okay? So the first thing we just need to know is that we're going to have this. Now, you guys are really lucky because back in the day, I don't know when I got soft, maybe 8 years ago, maybe a little bit longer, I don't know, I lose track of time now. I used to make you memorize these ions because you need to be able to recognize them, that when it's SO4, that it's sulfate, that it's not sulfur tetraoxide. You need to know that SO4 is a polyatomic ion, that it's a single unit. You need to know that ClO4 is perchlorate. All right, now there were tricks. There's only one polyatomic cation, that's NH4+. All your cations are monatomic, meaning what? Monatomic. Just one atom, okay? Al3+, Ba2+, Ca2+, chromium 3+. Okay, so there's only, monatomic. There's only one polyatomic cation, but there's a plethora of possible negative or anions that are polyatomic. Okay? And up there, we're going to learn out how the ions are named. So there really was 13 that you had to memorize. But nowadays, we've got soft, you guys, we're going more application and trying not to memorize. So I'm going to give you a sheet probably tomorrow of common ions, and you just have to be able to recognize them, know to look. Okay, but you have to be able to be real familiar with those. Okay, so they're going to be big. This is going to be real important as far as in our naming and writing formulas for ionic compounds, of being able to identify the polyatomic ions and name them. A special type of ion. When we look at this OH minus ion, what's the name? Look up here on this chart. What's the name of the OH minus? I recommend you kind of look at the third column. It's hydroxide. It's the hydroxide ion. Okay? Now the hydroxide ion is a special ion. When the hydroxide ion is combined with a metal, any metal, but predominantly groups 1 and 2, we call it a base, opposite of an acid. Now, what's group 1 called? What's the name of group 1?
Alkaline.
Alkali. What does alkali mean?
Water based or something. Isn't it water?
It's not water, but the second part of your definition was base.
Oh.
Okay, alkaline, if something's alkaline, it's basic. What does that mean about its pH?
Very low.
It's high.
What's neutral on a pH scale? 7. So base is going to be anything above 7, and that's going to be what we talk about kind of at the end of the year. Okay, but a base, it's the presence of this ion in solution that makes a base a base. That's what gives it its alkalinity. That's what makes it have the characteristics of a base, is this OH minus. And we know what ion is present in an acid. We're going to learn this at the end of the chapter, but I'm going to foreshadow here. Anybody know what ion is present in all acids? Go ahead again. Get a quarter every time you open the door. Anybody? Yes, sir.
Is it like some ion sulfur?
It doesn't have sulfate in it, but I mean, there's a lot of acids that have sulfur in it. Just put that on the desk, please. And then give her one of those. You see how they're kind of grouped? They're kind of sorted. Okay.
Oh, here's the other one.
Oh, I already gave her one? Never mind. I didn't realize I was thinking ahead so well. Okay? It's H plus, okay? All acids have an H plus ion. So you've heard that acids neutralize bases and bases neutralize acids, right? You've heard that in the past in your life? Yes? No? That acids neutralize bases, bases neutralize acids? Please tell me you've heard that an acid neutralizes a base. What happens when you have too much stomach acid? What do you take? Which is Tums, which are called what? They're called antacid tablets, right? What's ant mean in antacid? Not. Opposite, right? Ant is the opposite. An antacid is a base. It's going to neutralize that stomach acid. Bases neutralize acids, acids neutralize bases. Because if I put H plus in with an OH minus, what am I going to make? I know, but what compound?
H2O.
H2O, H-O-H, H2O. H plus OH minus is going to make neutral water. The presence of H plus in a solution makes something acidic. The presence of OH minus in a solution makes it basic, giving it the unique characteristics that they have. You put them together though, they combine and just make neutral water. Now we learned this in chapter 6, but all other ionic compounds are called, what's a common name for ionic compounds? Chapter 6.
Salts.
Very good. Okay, salts. That's just a common name. So my finger, I've had the infection in my finger, my cuticle, which finally is going away. It's getting better. Finally got it to open up and kind of gross, but it got all the infection out. But I had to soak it in Epsom salts. Magnesium sulfate, MgSO4, an ionic compound. Salt substitute, KCl, we made it in our lab, okay? It's, it's a salt. Any ionic compound is gonna be called a salt. Speaking of labs, I've already talked about your labs, right? They're due Monday, and we went through all that? No? Okay,
Yeah, you went through the day we did Monday.
yeah. I thought I did yesterday. Did we do we did the lab on Tuesday. Today's Thursday. So yesterday is when I kind of talked about it.
No, we didn't really have the time, actually.
Okay.
We didn't have the time.
All right, well, I'll talk about it in just a little bit. I want to get through this and then I'll talk about it.
So we talked about the.
They're due on Monday regardless, okay? If I don't have a chance today, I'll for sure at the start of class tomorrow. But they're due on Monday, just for the record. So, in order to be able to write formulas, we have to do this thing called oxidation numbers. We have to understand oxidation numbers. Now, we already learned the periodic trend. Theoretically, I defined it, you're supposed to know what it is. Okay, but what is the charge? What charge does group 1 tend to form? Plus 1, that's its oxidation state. Plus 1, what does that mean, plus 1? It wants to lose an electron. Okay, these are all going to be plus 2. Okay, we'll skip over these. Now they have little black numbers above the symbol that down here tells me that is its oxidation state. We're going to learn how to use those in the next couple of days. Okay, but what's the normal oxidation state of group 13? Plus 3, plus or minus 4, generally plus 4, and then minus 3, minus 2, minus 1. But when you look at nonmetals, again, I like the word plethora, an overabundance of a plethora of possible positive oxidation states. Okay, so we've got to talk about what does that mean. Okay, so as we go through this, we have to understand what oxidation numbers mean, and then we're going to have to be using these every time we write formulas for compounds. We need to understand how all this works. Okay, so the first thing is that elements in their natural state, pure gold, pure silver, pure copper, pure sodium, pure potassium, pure anything, the oxidation state is going to be 0. It's not until it goes to combine with something does it want to gain or lose electrons. Okay? So natural state includes our diatomic. So if we talk about H2, N2, O2, F2, Cl2, Br2, or I2. If everybody takes a breath right now, what are we breathing in?
Oxygen.
Oxygen, it's O2. That's the natural state. Its oxidation state is 0. Okay, that's what we say it is. Nitrogen, oxidation state is 0. Okay, that's its natural state, N2. Those 7. Remember, it starts at number 7. It makes a 7, and there's 7 of them. But then we add in hydrogen over here for astatine because astatine's radioactive and don't play well with others. And so anything that ends in gen or ene, G-E-N or I-N-E, is going to be a diatomic molecule in nature. That's its natural state. Oxidation state is 0. Okay? Now, oxidation state. I'm going to go ahead and just define this up here. We already did it, but it's the number of electrons an atom tends to gain, lose, or share. This is going to be the key thing, sharing, that we're going to focus on when forming a compound. When forming a compound. How much do they tend to gain, lose, or share?
It like depends on their periodic table placement.
That's right. Okay, and it's all about their valence electrons and how many valence electrons they have. And I'm going to get into that in great depth here right now. In ionic compounds, that's when they lose and gain, right? But covalent compounds is when they share. Elements gain or lose only a set amount. These all metals are going to lose 1, these are all going to lose 2. So the oxidation state is, so for sodium, is +1. But then when it loses 1 electron, it forms a 1+ ion. Magnesium's oxidation state is +2. It tends to lose 2, but when it actually loses them, it forms a 2+ ion. So for ionic compounds and for ions, the oxidation state and its charge is the same. So the oxidation state of a monatomic ion is the same as its charge. So there's no real difference. Gaining and losing. It's the sharing that kind of gets confusing.
So, do oxidation numbers really only apply to ionic compounds?
No, they're really most important in covalent compounds. Because in ionic compounds, the charge and the oxidation state are the same thing. Okay? So it's what does it tend to do versus what did it do? It tends to lose 1 + 1. What did it actually do? It lost 1. Now we say 1+. Okay? That's the only difference. So, and again, it doesn't matter really where you put the sign. But it's when we share. Okay? And I'm going to kind of go through in here, but then I'm going to kind of go and explain it in more depth. In a neutral compound, what do you think the charges have to add up to? 0. So the sum of the oxidation numbers in a neutral compound is 0. Key word being neutral. So positive has to equal negative. So when we're writing formulas, we're going to end up having positive ions or positive compounds and negative ones. But the charges have to add up to 0. Their oxidation states have to add up to 0. Now, even in that, some can have a positive oxidation state, some can have a negative. The more electronegative element is always going to be, what do you think? More electronegative is going to be negative or positive?
Negative.
It's going to be the negative. And the less electronegative element is going to be positive. I'm going to give you examples of that too. And then lastly, in a polyatomic ion, and it really should be common here, I don't know why I didn't put the in there, the oxidation numbers equal the charge for the particular polyatomic ion, but they still act as a single unit. Alright. So let's talk about what all that means. If I look at HCl, and I draw the Lewis dot structure for it, chlorine, 7 valence electrons. How many does hydrogen have? One. So hydrogen comes in here, and I'm gonna put electrons and electron, electron, but I'm just trying to show the source of them, okay? So, how many of chlorine's electrons are involved in bonding? One. But in HCl, they're just being shared. It's a covalent bond, it's not an ionic bond, so it's not really a transfer. But chlorine is sharing 1 electron. How many electrons of hydrogens are being shared? One. So, hydrogen has got 1 electron, chlorine's got 1 electron, but chlorine is more electronegative than hydrogen. Chlorine's one of our big 4. Phone call. So chlorine's the more electronegative, so we say that chlorine is -1 and hydrogen is +1. That tells me that chlorine's got 1 electron involved in the bond, hydrogen's got 1 electron involved in the bond. But I can also have HClO. Now, in this one, remember, where's the hydrogen going to attach to? To the O. Okay, so now I have chlorine, still with its 7 electrons, and I'm going to put the odd one there. Oxygen can come in here with its 6 electrons, and then the hydrogen can come there and attach to the oxygen. Okay? So when I want to talk about oxidation states, again, hydrogen has how many electrons involved in bonding? 1. It's with the oxygen, it's got 1, but oxygen is more electronegative than hydrogen, so hydrogen is going to be the +1. Chlorine has how many electrons still involved in bonding?
1.
Just 1, okay? But it's with oxygen now, which is more electronegative, oxygen or chlorine.
Oxygen.
So what does that mean about the charge on the chlorine? It's going to be a positive. So chlorine's now going to be +1. And then oxygen has how many electrons involved in bonding? 2, right? So it's going to be, but it's the most electronegative, so it's -2, but altogether it adds up to 0. Now, oxygen did not gain 2 electrons. So if we said 2-, that indicates that it's an actual transfer of electrons, that it's an ion. Here, -2 tells me it's just got 2 electrons that it's sharing with other elements. It's minus because it's the most electronegative. What's the only one element that's more electronegative than oxygen? Fluorine. So oxygen is almost always -2. The only time the only one compound it would be positive is in OF2. Then it would be +2 rather than -2. Still have 2 electrons, but plus because fluorine is more electronegative. Every other compound in the world, oxygen is going to be minus, and it's almost always -2. But now we can have HClO2 though exist as well. Okay, so HClO2. How do I get HClO2? Well, oxygen has 6 electrons. Oxygen is just an electrophile, a lover of electrons. Oxygen wants to bond with anything and everything as best as it can. So the electrons shift around, and we can have this bond that looks like this. We call that a coordinate covalent bond. We did that real quickly in chapter 6. Now, electrons and electrons and electrons, so sharing a pair of electrons between the two, sharing a pair of electrons, there's no difference in this bond and that bond, except that both electrons came from the chlorine. But now how many chlorine's electrons are involved in bonding? 3. Okay, can somebody else other than Edge give me an answer? Okay, 3. So we got 3. So when I go and I look at the oxidation state, hydrogen is +1. How many of oxygen? Oxygen now has, each oxygen gets credit for 2 electrons. It's 2 electrons being involved in bonding. Okay? So oxygen's always -2, but we have 2 of them, so what's the total negative? -4. So if it adds up to 0, what's the oxidation state of chlorine have to be? +3. Because it has that up to 0. Well, what does that +3 tell me? It tells me that chlorine's got 1, 2, 3 electrons involved in bonding. It didn't really lose 3. It's not an ion, so this oxidation number is way more important for sharing of electrons. How many electrons are involved being shared? And since a lot of these have lone pair, they can share with the oxygen. So we can make HClO3. Well, I can put another oxygen right here. The same coordinate covalent bond. So now how many of chlorine's electrons are involved in bonding?
5.
5. So it's really in the +5. That's why I erased the L there, sorry. That's the chlorine. So, but I can figure that out without drawing the Lewis dot structure, because what's the charge oxidation state always of hydrogen? Try again.
Plus 1.
+1. What's it always for oxygen?
Minus
-2, but now I have 3 of them, so it's going to be
minus 6.
-6. But if it has to add up to 0,
It'll be
that'd be +5. But that tells me again that chlorine's 5 electrons that are involved in bonding.
Is it ever happened like it doesn't equal 0?
Only if it's an ion, and I'm going to get to that one in a second.
But against, if like for chlorine, does it change? It's like depending on like the molecules around it.
That how many, what all's bonded to it. So now, HClO4, that fills the last spot. So now how many of chlorine's electrons are involved in bonding? 7. How many electrons, valence electrons does it have? 7. So now we're max. So 7 is the highest oxidation state for chlorine. But chlorine's the 3rd most electronegative element. So when's the only time it's going to form these positive oxidation states?
When it's with oxygen.
When it's with oxygen. Fluorine, you know, it can make HF, it would be it can make CLF and be +1, but it can't do all of these possibilities because fluorine has 7, it can't share a lone pair like the oxygen can. So it's really just these unique compound right here, the HClO, HClO2, HClO3, HClO4, that chlorine is going to be in these +1, 3, 5, and 7. Every other compound in the world, what's chlorine's oxidation state going to be? Just -1. Okay? So it's got all those positive numbers above the symbol, because it can do them when it combines with oxygen like this, but most of the time it's going to be -1, because it's going to be the more electronegative element. But again, that doesn't mean that it's gained electrons. That's how many electrons are involved in bonding, and the more electronegative elements negative, the less electronegative elements positive. Okay? But what if we have an ion? So if I have SO4, 2-. What does this say right here? In a polyatomic ion, what? The oxidation numbers equal
The charge.
the charge. So instead of adding up to 0, what do the oxidation numbers have to add up to?
It's like -2.
-2. Okay? So what do we know oxygen always is? -2. So we have 4 of them.
-8.
-8, but we have to know it has to equal -2, so what must sulfur be? +6. Okay, does that mean sulfur lost 6 electrons? No, that just means sulfur has 6 electrons involved in bonding. So again, if I do the Lewis dot structure, sulfur looks like this. I can put an oxygen in here with its extra electron, an oxygen in here with its extra electron. But now I can do those coordinate covalent bonds, and I show that all 6 of sulfur's electrons are involved in bonding. But I can also have SO3, 2-, which means, well, I'll just take one of these away. Now how many of sulfur's electrons are involved in bonding? 1, 2, 3, 4. But I can figure that out here, because what's oxygen's oxidation state? -2. We got 3 of them, so it's -6. What does it have to add up to? Well, it has to add up to -2, so sulfur must be, somebody says, +4. Okay? But notice it always goes in increments of 2, because of the way oxygen can share these lone pair. So when you look at phosphorus, it's +3 and +5. But also notice that the highest oxidation state is the number of valence electrons it has. It can't share more than it has, unless it's the US government. And so, but Elon's taking care of that supposedly, getting rid of all the government waste, so we're hopefully gonna balance the budget. We'll see. A lot of dust getting stirred up here these last month. All right, so let's just, real fast, we have 5 minutes. If I give you H3PO4, what would be the oxidation state of phosphorus in H3? Just put this right there at the bottom. You got a little bit of space here. Just underline, find the oxidation state of phosphorus in H3PO4. What's this quote charge, but its oxidation state going to be? It's not really a charge. It's not losing or gaining. It's how many are shared.
Is that thing on the left an H?
Yes, that's an H. Sorry. I'm writing quickly. Don't say the answer yet. Let other people figure it out. But then I'll call on you in a second. Okay? What did you get, Darsh?
Plus 5.
+5. That is correct. How did you get that?
I knew oxygen was -2, so that'd be -8.
Okay?
And I knew hydrogen was +1,
And you had 3 of them, so it's total of,
+3,
and it all has to add up to
0.
0. So hopefully without a calculator, we can just eyeball this and see that this must be +5. All right, but what if I gave you, I already just did that one. What if I gave you BrO2 -1? And we just want to know what bromines is. I need a female to tell me the answer to this one. Go ahead, Julie. +4. How'd you get that?
Because
Let's see if it is +4.
the oxidation state of
Oxygen is,
-2, but you multiply that 2 or something.
so it's -4, but what does it all have to add up to?
Sorry, I didn't see the negative.
Yeah, it's a -1 right here, so what,
it'd be, wait, so it'd be +3.
+3. +3, not +4, because for an ion, polyatomic ion has that up to the charge. Now, here's the question. How do you know if it's a compound or if it's an ion? What's the definition of an ion? Charged particle. So what's ion gonna have on it? Charge. If I just write, look, if I just write SO3, is that an ion? No. That's a compound, sulfur trioxide. But I could write SO3 2-, now it's an ion. If it's an ion, you have to write the charge. Okay? You have to write the charge. So tomorrow, we're gonna come in and we'll start talking about how we use these then to name and write formulas for ionic compounds.
What about the lab?
I'll talk about it at the beginning of class tomorrow, but make sure you remind me to do that, because I did it in the other 2 classes. All right, y'all have a wonderful day and go Jags.